All right, so now we want to graph circles and ellipses. So let's start with circles and then talk about how they relate to ellipses. So first, remember that the general form for the equation of a circle is y squared, well, let's start with x squared plus y squared equals r squared, where r is the radius. So in this case, I'd be looking at a circle with a center at the origin, some radius value r, and then the circle would just carve out all the points equidistant from the center to make the circle. Now we can also translate a circle by moving it up and down on the x and y axis, and we can dilate a circle by making the radius larger and smaller. So if I were to take x minus h, and we're used to seeing this from functions, right, where x is cattywampus, we would move in the opposite direction of whatever's listed here with the x, and then y, watch this, minus k, so k still controls what happens on the y-axis, but k is also cattywampus in a conic section, equals whatever the radius is squared. And so this would dilate the radius. If the radius changes, the circle would get smaller or larger. And h and k, both being cattywampus in this case, would translate the circle, the center of the circle, up and down and back and forth on the x and y axis. So let's do an example. Let's start with a graph so we don't get something wonky looking. And let's do, well, let's see. Probably dangerous, but I'm going to make it up. Let's say x minus 3 squared plus y plus 2 squared equals 8. Okay, well, that works pretty well because we can already see that x is cattywampus, and so the lines of symmetry for this circle, and I'm going to draw them in, would be at the line x equals positive 3, and the line for the y-axis is y equals negative 2, not the y-axis, but the horizontal axis of symmetry. So we know that the center of this circle, the circle is, man, that's hard to say. The circle is centered at x equals 3 and y equals negative 2. So that's the center. But what are we going to do about that radius? Well, 8, we know that what we want is r squared. So if I look at r squared equals 8, that means that r equals 2 root 2. And so my radius then is 2 root 2. Not a number I like to look at, but definitely something I can work with. So let's find the points at the far right and left and the points at the far bottom and top of my circle, and then I can sketch it in pretty easily. Well, since the center is at 3, negative 2, I know that all I have to do is start for the points on the x-axis, right? Because the radius is 2 root 2. And so no matter what, every point is going to be exactly that distance away from the center. So my center starts on the x-axis. My center starts at 3. And then I want to go 2 root 2 farther. So that puts me at 5. Well, let's be a little bit more precise. That puts me at 3 plus 1, 2, and root 2 is going to put me just a little bit past 3 root 2. So I'm at 3, 4, 5 root 2. Oh, yikes. Okay. Now in the other direction I'm going to go 3, take away 2 root 2. So I'm going to back up 2, right? And then go a little root 2 more. So that looks about right to me. So now let's do the same thing in the other direction. If my point, I know on the vertical plane or on the vertical axis, my point is already at negative 2. And if I go 2 root 2 up, that's going to put me at 0, and a little bit more will put me at root 2 on the y-axis. So at root 2 on the y-axis. And then the same thing in the other direction. I start at -2, -3, -4, -4 root 2. And you can see just by looking that that actually makes a really nice circle. Not that I'm going to be able to draw a really nice circle, but it actually makes a really nice circle. All right, so that's basically circles in a nutshell. No big deal, easy peasy. It's almost exactly the same thing as graph translations with functions, but nothing really tricky to do there. Just have to do some simple addition, subtraction to find your vertices. Now, we got to look at ellipses. Now, ellipses come with a lot of new vocabulary, and they come with some new equations. So let's start with the equation of a circle, and we're going to use the translated form of the equation of a circle to talk about an ellipse. Well, the translated form is x minus h squared plus y minus k squared equals r squared. But in an ellipse, we're not going to have the same radius. And by radius, I mean if I squish a circle bigger, I get an ellipse basically by squishing a circle. So if I go from the center out to here, if I were to call that the radius, well, going up, I don't get the same value. So using language incorrectly, or using the math language incorrectly, but saying the same thing, I don't have the same radius in the vertical direction as I do in the horizontal direction on an ellipse. So I'm actually going to solve my equation for 1, and I'm going to have different values as denominators so I can do my squeezing, because just like on the parent graphs, remember, fractions make graphs either squeeze or stretch. So that means I have some a squared and b squared. And so that means I'm going to squeeze the x-axis one amount, and I'm going to squeeze the y-axis some other amount. And that makes an ellipse from my equation of a circle. Okay, let's do one, and there's a whole bunch of vocabulary that'll come up and a whole bunch of cautionary notes. So let's graph the ellipse. X minus 3 squared plus y plus 1 squared equals 1, but under the x ratio, x is in a ratio with the number 36, and y is in a ratio with the number 9. So FYI, this is example 1, I think, in your textbook. I decided to use the same example because while none of these concepts are difficult, it's a lot. And so you might be useful to have two different references for the same problem. Okay, so let's figure this out. First, I'm going to want a new graph, or actually a new plane that I can graph my ellipse on. And then I'm going to want to rewrite this equation, right? Because I have an a squared in the denominator here and a b squared here, just like I did over here where I had r squared. I wanted to find out what r was. So I'm going to want to find out what the a and b values are. So in this case, I have a equals, oh, let's use another color. I have a equals 6 because a squared is 36, and b equals 3 because b squared is 9. And then I want to find a special c value that goes with working with ellipses, a special c value. And that value is found by using the formula c squared equals a squared minus b squared. Now, you're thinking right now that I've made a mistake. No, Marla, it's a plus. It's a plus. The Pythagorean theorem has a plus. But this is not the Pythagorean theorem. This is the ABC relationship. The ABC relationship of ellipses, or for ellipses. And so the formula is different. You need to learn that, and that's why I've written it in lime green, our shorthand code for make a flashcard for this. All right. Then what else do we need? We have our center, right? We know where the center is. of our ellipse because it's been translated away from the origin, because the center uses the same x and y values, or uses x and y values in the same way that a circle does. So my center is at x equals cattywampus 3 and y equals cattywampus 1. And so I know that the center of my ellipse is at 3 and negative 1. Now, we've got to do some definition. If I'm looking at an ellipse, and this is just a general ellipse, not the one I'm graphing at this point, but if I'm looking at some ellipse like this, I have, just like with the circle, I have vertices, right? And I called these are vertices of a circle, right? That's a vertex. This is also a vertex. This is also a vertex, and this is also a vertex. So on an ellipse, I also have vertices. Let's see if I can make that a little bit better of an ellipse. I also have vertices. They just happen to be only considered vertices if they're on the longest part of the ellipse. So this is a vertex. And a vertex on the longest part of the ellipse called the major axis. Okay, so the longest part of the ellipse means that the major axis in this case is horizontal. In the picture I've just drawn, I don't know what's going to happen here for sure. Well, I kind of do, but you don't yet necessarily. So the major axis is the longest part of the ellipse. The minor axis then is going to be the axis of the axis of symmetry for the shortest part. Right? So that's the minor axis. And the vertices on the minor axis are called co-vertices. Okay? So that's a little bit of definition that has to be done. We're going to look first for the actual vertices, not the co-vertices, and we're going to look at how we might find them. So I want to find the vertexes. I don't even know how to spell that, let alone say it. Vertex is vertexes. Okay, vertices. I'm going with that. So we know already that the center of this ellipse is at 3, negative 1. So without putting a label in, just so I have room to work in a minute, I'm going to put the center here at 3, negative 1. And then making a quick glance and planning ahead, I noticed that I need my intervals on the x and y axis to be 2, just so that the whole thing fits on the plane that I've uploaded. So 3, negative 1 is actually going to fall here and here. So this is the center is at 3, negative 1. And now I want to find the vertices. So first, let's look. I'm going to sketch in something that's not necessarily the real place, but I can say, just so that we can kind of understand it, I can say that no matter what, for these two vertices, the y-ordinate is definitely negative 1. So I don't know what the x-ordinate is yet, but I know that the y-ordinate is negative 1. Okay, so I'm halfway there on both of those points. All I need to know is, so I know that the center is centered, hence the name, and so if I started at the center, then I know I'm starting at 3 on the x-axis, and I just want to know how much farther do I have to go on the x-axis to get to the vertex. So I need a number to add to 3, right? So this would be 3 plus some number. And the same thing in the back direction is 3 minus the same number. It has to be the midpoint. That's why we're calling it the center. So what would that number be? Turns out, easy peasy, since I'm talking about the x-axis, or the axis that runs in the direction with the x-axis, I'm talking about the x-ordinate, I'm looking at the number in the denominator, right? A for this denominator is 6. So 3 plus 6 is 9, and 3 minus 6 is negative 3. So I've now located my vertices, so I can erase all of this other gobbledygook and put in the actual coordinates of the vertices. So 2, let's see, 9, -1. So I'm at 2, 4, 6, 8, 9, and -1. And then -3, 2, 3, -1. And that kind of looks good, doesn't it? It looks like it's equidistant from the center. Cool. All right, now let's find the co-vertices. And what do you think we'll do there? Same thing. I see, yes, that's how you spell it. Okay, vertices. So the co-vertices then, right? What do I know about them already? Because those points are going to line up on this line, right? What I know about them already is that the x-ordinate is 3. I don't know the y-ordinate, but I know the x-ordinate is 3 in both cases. Okay, so what would y be? Well, y is going to be -1 plus some mystery number and -1 minus some mystery number to get me equidistant from that center. And what would the mystery number for the up-down value, like going up on the y-axis? Well, sure, it would be b. So -1 plus 3 is 2. Let's erase this stuff. Is 2. -1 plus 3 is 2. And -1 minus 3 is -4. And let's go ahead and fill that in here. 3, -4, and 3, 2. And so now I actually have, and I'm sure I won't do any better job with my ellipse, well, slightly better, I guess, than I did with my circle. And I can say that my vertices are at 9, -1, -3, -1. My co-vertices are at 3, -4, and 3, 2. Okay, and my major axis, being the axis on the longest part, the major axis is the line y equals -1, and my minor axis, oh, that didn't go in there well. My minor axis is the line x equals 3. The only thing I have yet left to put on here, whoa, what happened to my point? Okay, and so the only thing I have left to put on here is, remember when we did this in class the other day, we used 2 pins to make an ellipse, and we put the pins in locations that we called the focus or the foci. I don't know why stuff is disappearing and reappearing. Well, okay, I think I might have figured it out. Hopefully it'll stop happening now. And so the focus, we want to find the focus, and or the foci. Yep. And those have their own formula associated with them wherever they are. And the formula for them is very similar to finding the formula for the vertices. Since the foci only fall on the major axis, we're going to use the same formula, but instead of using, as what we did here, we took 3 plus a, right? Instead of 3 plus a, we're going to do 3 plus c to find the focus, and 3 minus c to find the focus. So 3 plus, we didn't calculate c. Well, let's calculate c real quick. So in this case, c squared, or c, equals plus or minus the square root of a squared, which is 36, minus b squared, which is 9, plus or minus the square root. 36 take away 9 is 27, and that reduces to plus or minus 3 root 3. Okay, so now we can make the put in the foci. So we know that the y-ordinate, just like before, the y-ordinate is -1 in both cases. But the x-ordinate is going to change, and the x-ordinate will change by 3 plus 3 root 3. So 3 plus 3 root, well, it's kind of right there, right? So, because that would be 3. And then 3 root minus 3 root 3. So 3 plus 3 root 3 is 6 root 3. And 3 minus 3 root 3 equals negative root 3. All right, so let's do one more example. And I know I've already been 20 minutes, but frankly, the first time I taped this video, it was an hour and 10 minutes and then 40, so I'm way ahead of the game. So let's do one that starts algebraically. Okay, so we want to graph this ellipse. It's not yet in the form that we like it to be in. And as we learned with parabolas, we just have to complete the square on both variables. So let's rearrange the equation so that we get our x terms and our y terms together. So I have 4x squared plus, oh, that's a minus 24x plus y squared plus 4y plus 24 equals 0. Okay, now I want to group my x terms together and I want to group my y terms together. And if I have a leading coefficient, I have to pull it out before I complete the square. So let's complete the square first on the x variable. That means I'm going to divide both by 4, and I'm left with an x squared minus 6x plus, because I'm completing the square, some new term minus the same new term. And then I guess I might as well do the y variable at the same time. So there's no leading coefficient, or there's no coefficient other than 1 on the y squared. So that's just going to give me y squared plus 4y plus the new term I make up minus the new term I make up plus 24 equals 0. Okay, so now I need my new term. Well, my new term is always b over 2 squared. And so b is -6 squared. Simplify inside, -3 squared. And then -3 squared is 9. The first one goes in the first spot, creating a perfect square that we can collapse, and the second one goes here. And then the second, for the y variable, I've got 4 over 2 squared, which is just 2 squared, which is 4. So 2 squared goes in the first one and 4 goes in the second one. They're both the same value. I'm adding it in, then subtracting it out. Okay, now let's collapse. So I have 4 times, well, the perfect square portion just collapses to x minus 3 squared. But the -9 has to be distributed with the 4, so it's a -36. So I'm going to put that out here, -36. I'm going to put it over here with my 24. So I've dealt with all the parts of the x term, now completing the square on the y term. The perfect square is here. So I have plus y plus 2 squared minus 4, which I'm going to put here with my constant values. Now I left myself more room, but that's okay. So I have 4 times x minus 3 squared plus y plus 2 squared equals, I'm going to subtract these to the other side. So 24 or 36 take away 4 is -40 plus 24 is -16. But if I subtract that or add that to both sides, then I get equals 16 on this side. Now I'm going to divide both of them by 16. So when I divide both sides by 16, I get a 16 in my denominators. 16 over 16 equals 1, and now I have my standard form for a parabola or an ellipse. Okay, one more simplification to do. 4 divided by 16 is really just 1/4. So I have x minus 3 over 2 divided by 4 plus y plus 2 over 2 divided by 16 equals 1. And I'm ready now to graph. So something to notice, unlike my previous graph, my bigger denominator is actually under my y value. And that's important when you're graphing conics, because whichever one has the biggest denominator becomes the major axis. So this time I'm going to end up with a vertical ellipse, meaning that my vertices are going to be in the up-down direction and my co-vertices are going to be in the right-left direction. And so we have to make adjustments when we're graphing this to fit that. So let's get our details first. A squared, we just typically call A whatever the biggest one is. And so A squared equals 16. So let's start with our center, and we know for a fact that our center is at XY, right? The translations, and so X being cattywampus. We know that it's at the point +3, and Y being cattywampus, -2. And so these are also our axes of our major and minor axes, so hard to say. And so I have an axis at x equals 3, and I have an axis at y equals -2, representing the center at their intersection. And then all I want to know now I know it's an up-down, so I know I'm looking for my vertices to be on the vertical axis. And so I just want to know how far up from -2 do I have to go to get to one of my points on the vertex. And remember, those are represented by -2. So let me write this out a little bit. Let's write our vertices. So I know, no matter what, I know that the x coordinate for my vertices is going to be 3. Or the x ordinate for my vertices is going to be 3, no matter what. All I need to know now is where am I on the y-axis. And so I know that my y-ordinate starts at -2, and I want to add to it something to get up here, and then -2 take away something to get down here. And what are the plus minus? They're just my a, right? Because I'm on the y-axis, I'm going to add 4. So -2 plus 4 and -2 minus 4. So that means that my vertices are at 3, 2, and at 3, -6. So 3, 2, and 3, 1, 2, 3, 4, -6. 1, 2, 3, 4, 1, 2, 3, 4. Ooh, optical illusion. That doesn't look evenly spaced, but it is. I checked. All right, so now let's look at our co-vertices. This time I'm going to use 4. So my co-vertices are going to be, and let's use the logic of it, we know they're going to be on the minor axis, which is the y, which is the horizontal axis in this case, because it's the skinny part of our ellipse. So the minor axis, so I'm starting at 3, nope, totally right, just panicked a minute. I want to first label, I don't know necessarily what the y ordinate is for these yet. I mean the x ordinates are, but I know that the y ordinates are at -2. So the y ordinates are at -2, and the x ordinates are at 3 plus something and 3 minus something. But what is that something? Well, the something is b. B is the minor axis. B is associated with the smaller number, and so b in this case is 2. So I'm going to add 2, and then I'm going to subtract 2. And so my coordinates for the co-vertices are at 3 plus 2, which is 5, -2, and at 3 minus 2, which is 2, -2. So 3, 4, 5, -2, and at 2, -2. And that looks just about right, doesn't it? That would be it right there. And now the only thing we need to figure out now is where are, I'm just going to sketch them in, the foci. So the foci, remember, they mimic, because they're on the same axis as the vertices, they're going to mimic the behavior of the vertices. So they're both at 3 and some number, and 3 and some number. So I've got a plus some number and a minus some number, but they're offset from the center. The center here is at -2 plus something and -2 minus something. And what is the plus and minus that we use for the foci? We use C. So -2 plus 2 root 3, just got it from right here, and -3 minus 2 root 3. And so we can say that the coordinates for the foci are 3, -2 plus 2, root 3 just leaves a root 3, and at 3, -2 minus 2 root 3 is -4 root 3. Okay, so I'm finally done. I know that turned out to be 31 minutes, but trust me, it was, well, better put together and faster than my first 2 attempts. The most important thing, and again, I use the examples from the textbook for a reason, because I find understanding conic sections is so much easier to do if you think of it in terms of you're looking for things, where are they? Your book has some very specific H plus or minus K, C kind of things. It has lots of little formulas for you, and there's one for the major axis ellipse, and there's one horizontal major axis ellipse, and a different set for the vertical major axis ellipse. And I find it's easier just to understand what you're looking for and where it goes, because it tells you what to find. In this case, since I haven't labeled it, we can kind of backtrack a little bit. In this case, I knew it was a vertical axis. The vertical axis was major because it was associated with Y. Y is the vertical axis on your plane. And so we know that it was going to be one of these long, skinny, tall, skinny ellipses. Then once you know that, then you know that A is the big number, B is the small number. You have a calculation to find out what C is once you've established A and B. Perfect. We did that. Then identify the center. Well, it's the intersection of the axes of symmetry, and those come right out of the equations in exactly the same way they do for parent functions, except that in this case you have to remember that not only x but y also operate in the opposite sign of what's visible in the equation. So x and y are both cattywampus for a conic section. Once you've decided that, you have the center, and you want to ask yourself, well, to find the covertices, I'm looking at the minor axis, so it's going to be the center plus or minus something. It has to be plus or minus the minor number, which in this case is 2. And to find the vertices, it's going to be the center plus and the center minus the major number, which is 16, which sorry, I said 4 and 16, but I really meant the square root of 16 and the square root of 4, so you want A and B. And then to find the focus, same thing. You're changing the y ordinate by adding or subtracting C to get the focus. And by looking at the picture, you know whether you're going to add and subtract to the x ordinate or the y ordinate because you're looking at the picture. So this is my favorite way to graph a conic or an ellipse. You're certainly welcome to memorize all those formulas, but I'm going with this method.